So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. Today, it's a particular pleasure to welcome Professor Will Horowitz from UCT. One reason why it's a special day, because he's the head of node of NITheCS at UCT. So thank you very much for that, Will. Yeah. But not only that, Will did his PhD at Columbia University a few months ago. And since 2010, he's at UCT. Yeah, and during his time in South Africa, he won many awards, yeah, from UCT, from the Royal Society, from the Claude Leon Foundation, yeah, and in particular, many local students, postgraduate students know him because he started the bursary program of the SA-CERN collaboration. And within NITheCS, he's been instrumental in setting up our South African Theory and Computational School, which every semester offers various courses at honors and master's level and so on and so forth. Yeah. And, and today he'll give us a very nice talk on cold temperatures. Yeah. And we are very happy that you are here, and we are very much looking forward to your talk. Thank you very much.
Thank you for a wonderful introduction. Thank you all for coming. It's a real delight to be here. As mentioned, I'll talk about the physics of 1 trillion degrees. So very, very hot, actually. And we'll talk about what we mean by 1 trillion degrees in a moment. Give me just a second here. Great. So if you were like me and had a high school chemistry course where a phase diagram was discussed, what we're then very familiar with the idea of the phase diagram for water. So here on the y-axis, we have pressure, and on the x-axis, we have temperature. And we're aware that water takes on multiple phases or different phases depending on the temperature and pressure that it is under. For example, at standard pressure, say around about here, below 0 degrees Celsius, then water is in a solid phase. Then something drastic happens at 0 degrees Celsius, and then there's a transition to a liquid phase. And then as we raise the temperature of the water to 100 degrees, again, something drastic happens, and one gets to a gaseous phase. And this is something that certainly when I was in high school and even through undergraduate times, thank you, I didn't really appreciate how profound these changes were. Because, and let me tell you why I think it's so profound. When we experience most aspects of everyday life, changes are continuous. I change something just a little bit over here, I get a small change over there. But these first order phase transitions, where one has solid water below 0 degrees Celsius from negative whatever up to just below 0 degrees Celsius, and the water is a complete solid. And then, and what is a solid? So a solid is an object that is incompressible and maintains its shape. And then at 0 degrees Celsius, there is a discontinuous change to a liquid. So something that is still incompressible but takes the shape of its container. And the same thing happens between the liquid phase and the gaseous phase. And that's really interesting. And it's not even true for all the materials we see around us. If you change from water to maybe just a slightly different substance, say butter, then butter, when you take it out of the fridge, is very much a solid. But as it starts to heat up, it becomes more malleable. It has a continuous change from solid properties to once you put it into a pan and it melts, really melts, it becomes a liquid. There's a continuous change. It's what we call a crossover, which is what happens with water going from liquid to gaseous beyond what this is called the critical point. And so it's very interesting to categorize the properties of a substance in its various phases and the types of phase transitions that that material undergoes. Not being satisfied with just trying to understand the phases of water, what we'd like to understand is the phase diagram of nuclear matter. So the substance that comprises 95% or even 99% of all of the mass that we see in the visible universe is nuclear matter. And what kind of phases does nuclear matter have? And so we would like to talk about the emergent many-body properties of the strong force, which is to say nuclear matter, and to talk that through in detail. What does that mean? Well, we're familiar with the four fundamental forces of nature: gravity, the electromagnetic force, the weak force, which broadly speaking breaks nuclei apart, and the strong force that keeps nuclei together. And if we focus on the nuclear force, the nuclei are made up of protons and neutrons. And the protons and neutrons themselves are made up of quarks and gluons. If we zoom into the picture of, say, an atom, inside the middle of the atom, there's the nucleus. Inside the nucleus, there are protons and neutrons. Inside the protons and neutrons, there are quarks and gluons. And the quarks and gluons are analogous to electrons and photons that we're used to from the electromagnetic force. And under normal conditions, the quarks and gluons are confined inside the protons and neutrons. And the strong force, it's described by what's known as quantum chromodynamics. It's a very complicated theory, and it's under active research even today. We don't fully understand the theory of the strong nuclear force. And very conservatively, 9 years worth of Nobel Prizes have been awarded simply for discoveries about or related to the strong force. And even today, within the mathematics community, there's the Clay Millennium Prizes. These are $1 million prizes, which given inflation, it's less money these days than it used to be, but it's still a lot of money. And it indicates that there's a very important fundamental problem in mathematics, and in this case, mathematical physics, related to the strong force. And the short version of it is prove that there exists a mass gap, right? That we see protons and neutrons, that quarks and gluons are confined inside protons and neutrons. If you can prove mathematically, rigorously, that that always happens in a strong force-like theory, you will win the Clay Mathematics Prize. So that's the strong force. What do I mean by many body? If you are in first year physics, then you often deal with, say, a projectile motion, a single particle propagating along in a parabola. This is coming straight from Newton's laws. And we can see this manifested, for example, in a cliff diver. We can see the parabolic trajectory that this person is undergoing. So there's a manifestation in the real world of the concepts that we see in our first year physics class. And this also is true for electromagnetic forces, where you have a charged particle going through a magnetic field, and there's a helical motion. And we can see this manifested in the night sky if it's dark enough and we see the aurora. But many body physics is very, very different. You change entirely the kinds of questions that you're asking. No longer are you asking, what is the exact trajectory of a single particle as a function of time? And if we want to try to understand, for example, water, we know the fundamental theories. It's Maxwell's equations for electromagnetism and quantum mechanics. And if we apply Maxwell's equations in quantum mechanics to a single H2O molecule, it's really very boring. It's well understood. This object is going to vibrate, it's going to rotate. But now, if we don't look at the sketch of the phase diagram of water, but really look at the phase diagram of water that is extracted by precise experimental measurements, here's pressure and here's temperature, you can see it's an extraordinarily complicated structure. And what's wild is that all of this information that is presented in this phase diagram has been extracted from comparison to data or by measurement. And none of this has been found from first principles calculations. By the way, I should say, if at any point you have any questions, please raise hands, interrupt me at any time. Questions make me very, very happy. So here, the phase diagram from a theoretical perspective is not understood at all. And that's very interesting then. That's a problem that we would want to understand. And the techniques that we have for understanding the particle physics that we learn in first semester physics cannot be applied here because we have so many particles involved. That if you think, oh, I just put all of this on a computer and I can solve the equations of motion. The problem is that for any kind of macroscopic sized quantity of water, the number of molecules is of order 1 mole, 6.022 times 10 to the 23 molecules. And first of all, you'll never be able to determine the initial conditions of all of these molecules. But even if you were able to determine those initial conditions, to try to advance one time step numerically would take longer than the age of the universe. So it's completely impractical. So one has to change the questions that one is asking and change how one answers those questions. So instead of thinking about, for example, the exact location of each of the molecules of water, we ask about the collective behavior. What is the pressure of the water, the temperature, the compressibility? What kind of waves are supported on this material, in this case, water? But what's fascinating about emergence is that it's everywhere, and we can look at different types of materials. So over here in a very clunky looking video, which is making me worried about my next video, but in any case, in this video, we have a number of ants. And you could ask, by placing a penny in the ants and watching the penny drop at a certain rate, you could ask, what is the viscosity of ants? What are the collective properties of ants? And over here we have, in principle, a video, which is from an Oasis concert in Manchester in the UK. And what I would hope that you see, it's very difficult to see in this choppy video, I apologize, is that there's actually a wave which is propagating through the medium of human beings. And so you could ask, what is the speed of sound of humans? And what's even crazier is in the video, which if you want, I could send you the link. This is somewhere on some ancient YouTube video that I pulled up. So you see the wave propagating here through the people. And then there are these security guards that are in front of the people. And what's amazing is that the wave actually tunnels through the medium of no people and propagates through the people who are the security guards. They get pushed back by the transmission of the wave through the air. So that's amazing. And then, of course, there's the greatest mystery of all, arguably, which is how does consciousness emerge? So we have 10 to the 11 neurons. We understand how a single neuron works, but how does putting all of those neurons together lead to thinking beings that can ask questions about where their consciousness even comes from? And so, in some sense, these ideas that we're thinking about today, confined to the ideas or confined to the material of nuclear matter, have broad applications. So just like we understand a single H2O molecule, we understand the strong force in particle physics when there are just a few of these objects around. And no need to understand these plots in any real detail, except that the theoretical calculations describe the data exceedingly well. That's what this is supposed to convey to you, that when you have just a few nuclear particles, matter, just a few quarks and gluons around, then one is able to, in a very well-controlled way, predict the results of experimental measurements. And so here is our best understanding of the phase diagram of nuclear matter, where we have temperature on the y-axis, what's known as baryon chemical potential on the x-axis. Baryon chemical potential is just how hard is it to put a neutron in. Here's us. If we go out at low temperatures, high baryon chemical potential, so this is the center of neutron stars, and we expect that there's a phase transition to a color superconductor. So just like superconductivity with electromagnetism, we expect that there's superconductivity when it comes to the strong force, and that exists in the center of neutron stars. Then at very high temperature, very low baryon chemical potential, this is going towards the experiments that I'm interested in, the relativistic heavy ion collider in the United States, the Large Hadron Collider in Europe. And then up along this axis, as far up as you can go, is the early universe. And so what we'd like to understand is, what are the properties of the early universe, which would be nuclear matter at very high temperature, very low baryon chemical potential, and the properties of that matter as there's a trajectory traced out as the universe cools as a function of time. And then how is that imprinted on the large scale structure of the universe that we see today? All right. So why am I spending all this time thinking about nuclear matter? Why are my students thinking about this? Why are you in this colloquium when you could be outside where it's a beautiful day? Well, what are the unchanging physical laws of the universe that we live in? So we would like to understand the properties of matter, and we'd like to stick that in a book and stick it in a beautiful library for future generations. We'd also like to understand, what are the limits of the properties that materials can have in the universe. So for example, how perfect can a liquid be? And if you want to ask how perfect a liquid is, you have to ask, well, how do you measure the perfectness of a liquid? And it's measured in a quantity known as the shear viscosity to entropy density ratio. This is analogous to friction on, say, surfaces. So in some sense, a surface, the smaller the coefficient of friction is, the more perfect that surface is. And in a similar way, the smaller this eta over S, the more perfect a fluid is. And if we look at various types of materials, say water being one that we're the most familiar with, then in this dimensionless ratio, then water, which we think of as a fairly good fluid, the 8 over S is somewhere between 2 and 3. But when we go to, say, superfluid helium, what was previously thought to be the most perfect fluid, then in this dimensionless ratio, it reaches its minimum value at a little bit below 1. And what we find by looking at experimental measurements of nuclear matter at 1 trillion degrees, we extract a measured value of 8 over S, which is about 1/10, which is about 10 times better than the best superfluid that was ever observed before. And there's a question, which is, can one do any better? Is this the most perfect fluid that can even occur? And there's a lot of suggestions that suggest yes, that this number, this 8 over S, which is about 0.08, is very close to 1 over 4 pi. Why is 1 over 4 pi an interesting number? Because that 1 over 4 pi comes from calculations using string theory in 5 dimensions, which I'll talk about a little bit, at least superficially later on, suggesting that this, for a theory that is infinitely strongly coupled, that the absolute minimum value of this 8 over S is 1 over 4 pi. And that's really interesting. But there's other questions, which are, for example, is it due to just Heisenberg uncertainty, the uncertainty principle? Maybe that limits how perfect a fluid can be. So these are interesting fundamental questions. As mentioned before, we're going up to 1 trillion degrees, and the universe has a temperature. Right now, it's a few millikelvin, but as we go back in time, the temperature of the universe goes up. As it has been expanding as time goes forward, the universe is cooling. So if we go back in time, the universe heats up. About 300 to 400,000 years after the Big Bang, that is when atoms started to form. And it's only at that point that the universe became transparent to light. So as we look out at the stars in the night sky, we go back in time because we know that that light was emitted at some previous earlier time. But at some point, there's a limit. You can only look back so far because at some point the universe was opaque to light. And so if we want to learn about the properties of the universe at its earliest times, there's a limitation, fundamental limitation when it comes to light. We need to go to another way of measuring the properties of the universe. And what we do in my field is we look in the nuclear force. And with the nuclear force, we can get to a microsecond after the Big Bang, because at a microsecond after the Big Bang, the whole universe was at 1 trillion degrees. And that's the temperature that we're probing in high energy nuclear collisions at RIC and at LHC. And actually, I should say that this is the best game in town, that the earliest moments of the universe that can be probed are those moments that are probed by the nuclear physics that we are interested in. And then the last motivation that I want to talk about is connecting to other areas of physics. So for example, to plasma physics or what we call condensed matter physics. And the question is, how does the phase transition to material that starts as protons and neutrons, it collides 1 trillion degrees, is now quarks and gluons, and we call it a quark-gluon plasma. It's a deconfined plasma of charged objects. How does that quark-gluon plasma behave? Is it like a weakly coupled gas? So is it kind of looking like pluses and minuses with Debye screens? Or is it something very different where it's strongly coupled? And in the condensed matter realm, that strong coupling can be related to, for example, high temperature superconductivity, which is believed to be best understood in terms of a strongly coupled material. And so the techniques, the tools that can be used that we have been using to learn about the properties of corpuscle plasma, the phase diagram of nuclear matter at 1,000,000,000,000 degrees might be applicable to understanding more terrestrial questions about how certain metals behave and moving towards a resistanceless propagation of electrical current. Good. So how do we create these conditions of a microsecond after the Big Bang? Well, it costs a lot of money, and it takes thousands and thousands of people, but it's amazing that we can do this. And I think it's worth taking a moment to consider the achievements that we have achieved as a species, right? So we've gotten to the bottom of the ocean, we've gone to the moon, but we're also recreating the conditions of the very, very early universe. So here at Brookhaven National Laboratory, Brookhaven National Lab, this is out on Long Island near New York City. It's about 2.5 hours outside of New York City. There is a collider tunnel that was built, the relativistic heavy ion collider. And here in Geneva, there's the Geneva International Airport, which gives you a sense of scale. That's a 5-kilometer long airport runway. This is the Large Hadron Collider, where large nuclei are collided at about the speed of light. And these nuclei, they collide and produce thousands and thousands of particles, 15,000 particles, and they are detected by very large detectors. Here is the ATLAS experiment at the Large Hadron Collider. This is a CMS experiment at the LHC, and here the humans give you a scale. And I encourage you, if you ever get a chance, if you're in Europe, go by Geneva. The CERN lab is open to the public. Science outreach is an important part of their mission, so you can go and you can visit. If it is during the sort of December-ish months, the LHC is turned off, and you can actually go down in the tunnels, and it's a profound experience. Because one can see these images. Well, let me just personalize it. When I have seen these images in the past, I thought, oh boy, these are big experiments. But there's nothing like going and seeing it with one's own eyes and feeling small in comparison. And again, impressed in terms of what we've accomplished, where we've created the most complicated experimental measurements or experimental devices that has ever been seen. And here's an example, once it comes up, of some of our South African colleagues who have gone to CERN and conducted these measurements. And to give you a sense of the complexity of what we're trying to accomplish, these are the 15,000 or so tracks of the particles that emerge from one of these collisions that have all been observed by the ELISE experiment. And what's really amazing is that we're able to make sense of this. So how do we make sense of this? Well, the first thing that you would do is you just count the number of particles. So you're used to, I'm sure, protons, then also the deuteron, helium. Those are well-known objects, but then there are more exotic objects like pions, kaons, lambdas, cascades, so on and so forth. And what's interesting to see is that if you look at the relative abundances of these particles, that tells you something very specific about the temperature. If you've taken this statistical mechanics course, you just know that there's a Boltzmann distribution, e to the minus energy over temperature, and that T that you fit by looking at the relative abundances tells you the temperature of the material. And in this case, the temperature is 156 MeV. That was what was extracted. What is that in units that we know more and love? It's about 1,000,000,000,000 degrees. In Kelvin, in Celsius, in Fahrenheit, it's all very, very, very hot. And this was officially recognized by the Guinness Book of World Records as the hottest material that's ever created. How hot is this? What is 1,000,000,000,000 degrees? I don't have a good finger feel for that. Well, it's 100,000 times hotter than the center of the sun. So it's incredible. You know, one could talk about nuclear physics and the low energy physics, nuclear physics, which is Kuiberg physics, for example, and this is very fundamental, very high energy nuclear physics. What is the next thing you could do? Well, after you've counted the particles, you could ask, how are those particles distributed? And what's happening in these nuclear collisions is you have these two nuclei coming at each other at more or less the speed of light. They look more or less like flattened circles, well, flattened spheres, which become circles. And these two circles that then overlap have some kind of an almond-like shape. That's what's shown here, that there's some almond-like shape in coordinate space. And if this material then evolves like a fluid, then there are pressure gradients. And in the directions where the density changes the fastest is the regions of largest pressure. So you'll have more pressure in, say, the X direction than in the Y direction. So the material will preferentially blow out in the X direction. And so what you will see is then faster moving material, material with higher momentum in the X direction than in the Y direction. And then you could ask, how is this distributed? And this is again related to the physics of the universe. In a similar way, at the very start of the universe was seeded with various anisotropies, and those anisotropies were propagated as a function of time. And one can see the imprint of those anisotropies as propagated through time in the power spectrum of the anisotropies in the cosmic microwave background. And in a similar way, we look at the Fourier decomposition of the material that emerges in the detectors, which are coming from the initial lumpy material that was deposited when these two nuclei collided. And what we'd like to do is we would like to describe quantitatively these anisotropies, which are in the Fourier coefficients of, say, V2, V3, V4. And what you can do is you can have a very sophisticated relativistic viscous hydrodynamics model for how this material evolves over time. And you can, as a parameter, turn the crank on the viscosity to entropy density ratio. And as you turn that crank, this curve will be larger or smaller, and you will want to compare to the experimental data and then extract a value. And as mentioned, the value that one extracts is approximately 0.1. And that's very different from what naive theoretical calculations would expect. One would expect it to be more like 1. Whereas when one is doing these strongly coupled calculations, one sees that this is about 1/4 pi. And as mentioned, the shear stress or the viscosity is telling you about how easy it is for layers of this fluid to flow past each other, just like friction in our everyday world. Good. And as mentioned, we want to extract the values. We get a value of about 0.1, and we want to understand where that value comes from. Why is it sensible that it's close to 1/4 pi? And that's very interesting. Now, if you have fluid that is flowing incredibly freely, and you have these two nuclei that are passing by each other at essentially the speed of light, then there's going to be an enormous amount of vorticity that this material, this fireball that is created in these heavy ion collisions, is going to want to rotate. And it's going to want to rotate extraordinarily quickly. And what's interesting is that that rotation is imprinted on the polarization of certain particles. So this vorticity can actually be measured. And you could ask, okay, well, how fast do we think that this thing will rotate? And the extracted value is about 10 to the 22 radians per second. Now that sounds like a large number, and it is an extraordinarily large number. So tornadoes have an angular velocity of about 1/10 of a radian per second. That seems pretty fast to me. But then we can go to superfluid helium. That's about 100 radians per second. And then the fastest rotating object that had ever been seen before were superfluid nanodroplets at about 10 to the 7 radians per second. So this is 15 orders of magnitude faster rotation. Now, one thing you could ask, okay, this is rotating about 10 to the 22 radians per second. How much does the whole system rotate? Well, how large is the system? So nuclei are about 10 femtometers across, and that gives you a sense of a scale in terms of the time scale for the survival of this fireball. Working in natural units where the speed of light is 1, the time is about 10 femtometers. So about 10 times 10 to the minus 15 meters. And if we put the speed of light back in, 3 times 10 to the 8 meters per second, that says that the lifetime of the material is about 10 to the minus 23 seconds. so very, very fast. And so if I multiply this angular velocity of 10 to the 22 inverse seconds times about 10 to the minus 23 seconds, what I end up with is about 15 degrees. That's how much this thing rotates. So even though it's rotating extraordinarily quickly, it doesn't rotate very much. And this made the cover of Nature a few years ago. And continuing along this journey of extremes, how large is the magnetic field, right? So we have two nuclei that are very large positive charges because we stripped off all of the electrons. And these two nuclei are going past each other, again, essentially at the speed of light. And the size of the magnetic field is, again, enormous. It's about 10 to the 15 Tesla. And if we compare that to other values of magnets that we experience, so the Earth's magnetic field is about 50 microtesla. The largest terrestrial magnet that has ever been generated is about 50 Tesla. Neutron stars 10 to the 6 Tesla, and magnetars 10 to the 10 Tesla. And these magnetic fields are so large that even if you're in a distance about a solar system away from these objects, you literally could not survive. You'd be ripped apart by the magnetic field. And this is, again, 5 orders of magnitude larger. And we're generating this thousands of times a second in these heavy ion collisions. Okay, great. So hopefully I've made you think, this is very interesting. How do we study it in more detail? We've talked about some qualitative insights that we've generated. What about some quantitative insights? And there are several ways that you can do calculations in QCD and quantum chromodynamics. One is you just put it all into a computer and you discretize all of space and all of time. And this allows you to compute a large number of quantities of interest that can also be compared to data. And you see here an incredible success of these lattice calculations. And here we plot the entropy density as a function of temperature of nuclear matter. And you can see an enormous jump in the entropy at about 180 MeV. And this is a clear indication of a change of the degrees of freedom, the relevant degrees of freedom of the problem. And so this is an indication of a phase transition, that we're going from ordinary nuclear matter, say pions here, to something else out here. So we're learning something very interesting from these lattice QCD calculations, but we can't learn everything. For technical reasons, we're restricted to what are known as Euclidean correlators. And so we can compute things like pressure or entropy or the equation of state, but we can't learn anything dynamical about the system. On the other hand, we can do calculations in the usual way within perturbative quantum field theory. So you may have seen Feynman diagrams. So these are techniques that we can use to calculate certain quantities. Actually, we can calculate any quantities. One of which, for example, is the distribution of high momentum particles that are produced in the collision of very high momentum hadronic material. And the reason why I talk about very high momentum particles is because even though we can calculate any quantity, we are restricted to quantities at small coupling. So we need some kind of a large scale. I also talked about another method that we've used in recent years, and this is based on what's known as the Maldacena conjecture. And this is falls under the umbrella of ADS-CFT, so the anti-de Sitter formal field theory duality. And the idea is that your theory in d dimensions is dual to a theory in d plus 1 dimension. So for us, if we're interested in a strongly coupled theory of nuclear matter in 4 dimensions, 3 spatial dimensions and 1 time dimension, we go rather into a weakly coupled theory of gravity, so like Einstein general relativity, in 5 dimensions. We have an extra dimension. So we can again compute any quantity, but there are several complications that are involved, not least of which is it's very difficult to think about things in 5 dimensions. We also have questions about what theory we're in and how we might be able to apply these techniques. Then there's my favorite way to do a calculation, which is to give it to a student. And I throw my feet up on the desk. All right, that was a joke. Thank you to the few people who laughed. All right, so what do I do specifically? So I and my group work specifically looking at very high momentum or very heavy particles. So we try to focus on questions that can be addressed where there is a large scale in the problem. And the idea is that we're trying to use these particles as a femtoscope. So we made enormous advances in science as we were able to look at quantities on the microscopic scale with microscopes. So what we'd like to do here is to work on the femtoscopic scale. In medicine, if you are able to probe some material like the abdomen of a person using a number of different tomographic probes, you can create an incredibly detailed image. Here, one is using external X-rays, so a CT scan, while at the same time, this person has ingested some radioactive material, which is then generating internal gamma rays. And you can see this beautiful picture that emerges from those measurements. And we want to do exactly the same thing, that we have some kind of almond-shaped-ish material that is some kind of trillion-degree fireball. And inside of this fireball, on rare occasions, there are very high momentum particles that are created, very high momentum quarks or gluons, and they propagate out. And as they propagate out, they interact with the material, and then they lose energy. And so the spectrum of these partons, these quarks and gluons, is modified and ultimately measured as, say, pions or other types of fundamental particles that we know and love. And so what we would like to do is we would like to, in detail, measure these particles, these spectrum of these particles, the number of these particles and their distribution as a function of angle. And then we would like to hypothesize the properties of this fireball medium and make quantitative predictions for how the spectrum will be modified. And we want to compare that prediction to experimental measurements. So we're inverting this attenuation pattern to extract medium properties. And my group's part of this puzzle is doing that, hypothesizing about the properties of the medium and producing those quantitative predictions for how the spectrum is modified. And this gives you some sense of the idea. So there's the production of a very high momentum particle, and then there is the high momentum particle transitioning from a quark and gluon degree of freedom into hadronic degrees of freedom through a process known as fragmentation. And inserted in the middle is the interaction with the nuclear matter at 1,000,000,000,000 degrees. And the idea being that the matter might organize itself into Debye screen scattering centers. So there's some scale over which this matter is distributed in some way, and there's a mean-free path, so how far particles tend to propagate before they interact with the matter. And with those quantities, then one can predict the properties or the amount of energy that is radiated away from this high momentum particle. And this would be the weakly coupled picture of how this medium has organized itself. And we could swap that picture out for something completely different. For example, a picture that is strongly coupled, where we are now working, rather than 4 dimensions, we're working in 5 dimensions, where we replace the idea of a quark or gluon as a point-like object to now a one-dimensional object that is sweeping out a path or a world sheet in space-time, where momentum is flowing down the sheet and heating up a black hole that represents whose Hawking temperature then represents the temperature of the plasma that we're trying to model. And so if we focus on a perturbative QCD, a Feynman diagrammatic way of considering these energy loss, there are 2 types of energy loss. One is collisional or elastic. So this is a energy conserving process in first year physics, where we have 2 objects in, 2 objects out. And there's also a radiative energy loss. So this is a 2 to 3 process where we're explicitly emitting some radiation. And one can go through the process of thinking about what the scales are in the problem. This is an important procedure that you want to do in physics, is figure out if you have some kind of ordering of scales, which then allows you to make certain approximations to make the calculations tractable. And in the way of thinking, in the conditions that we expect in these quark-gluon plasmas at 1,000,000,000,000 degrees, we have a Debye mass, which is about a half of a GeV. The mean free path is about a femtometer. And remember that nuclei have a size of about, say, a radius of 6 femtometers. So a diameter of 10 femtometers. And so then we have an ordering of scales, which says that the size of the objects that one is scattering over is much, much smaller than the mean free path between scattering centers. And that's much, much smaller than the formation time. So I try to emit a gluon radiation. But as that gluon tries to become what we call on shell, or to separate itself quantum mechanically from the original particle that produced it, that radiation itself interacts with the material. And this re-interaction is unique to what are known as non-abelian field theories, which is to say quantum chromodynamics. You can't readily see this kind of process in electromagnetism. And then all of these scales are small compared to the size of the system. And so what this tells us is that we are in a very particular area of radiative energy loss, which is known as the deep LPM regime for Landau, Pomeranchuk, and Migdal, who thought about this many, many years ago. And that's in contrast to the beta Heitler limit that one knows and loves if one had Jackson EM for their advanced electromagnetic electrodynamics theory. And in the beta Heitler limit, the energy loss grows linearly with momentum. And in this deep LPM regime, where there is a suppression of the emission of additional radiative quanta, that linear growth in momentum is softened to a log. And that has very important consequences. That in particular, if I compare this reasonable energy loss calculations to data, where the specifics about what these various quantities mean is not so important, but just to show that we have a good description of a large variety of data over many orders of magnitude, this particular growth, this logarithmic growth in energy, is very important in describing the data. So what I would like to convince you of is that we have at leading order, a very good description of all of these observables at very, very high momenta. And so what we'd like to do is we would like to improve these calculations as our next steps, as we try to understand the nature of this material at 1,000,000,000,000 degrees. And there are a number of different ways that one could think about improving these calculations. And I wanted to just focus on one, which is to think about small systems. And that's very interesting for a few reasons. One is just in terms of these experimental measurements. So the systems that I showed you earlier are large systems. So gold nuclei colliding, lead nuclei colliding, they're large in terms of nuclear matter. So it's on the order of 10 femtometers across. But what people are finding is that the signatures that we associate with the production of this quark-gluon plasma, this new form of matter, that we definitely see in these large systems, that all of these signals we are also seeing in small systems. So here, one is using these sophisticated relativistic viscous hydrodynamic calculations to describe the angular distribution of material at low momentum, here that what's known as V2 and V3. And you see a very good description of data in, say, helium-gold collisions, deuteron-gold collisions, or even proton-gold collisions. So systems that are now 1 femtometer across, not 10 femtometers across. One can look here about what's known as strangeness enhancements. So there are the types of quarks. There's up-down quarks that form protons and neutrons, and then there are strange quarks that form other particles. And there's a long-standing prediction that in a deconfined matter at very high temperatures, there's going to be more strange particles than you would have expected. So this is an increase in the yield of strange particles as a function. And now here it's plotted, this ratio of the amount of strangeness. So from a single strange particle to doubly strange particle to triply strange particles. And the enhancement grows with the amount of strangeness in the particle. That amount of strangeness enhancement grows with the multiplicity, the number of particles that are measured in the final state, the number of, say, 15,000 particles that are measured in very central lead-lead collisions. And what's amazing is that this enhancement that is observed, that enhancement is agnostic to the collision system or the size of the system. It only cares about the number of particles in the final state. The same thing can be said about quarkonium suppression, another measurement. And so the question is this new state of matter, this quark-gluon plasma that we see in large systems, do we also see it in small systems? But this also comes back to the question of emergent properties. And emergent properties, how many particles do you need to have a notion of a pressure or a temperature or a wave? That we used to think that you needed something like 10 to the 23 particles in order to think about the sound waves in this room and the air in this room. But now we're talking about coming back here. We're thinking about more like 50 particles. So changing by a factor of 10 to the 23, the number of particles needed in order to support emergent many-body dynamics. So looking at this within the context of heavy ion collisions and nuclear theory, one of my students, Cole Faraday, actually related to the Faraday through a long chain. So he is looking at, say, the temperature and size of these small systems and seeing that, yes, they are very different from the large systems. But nevertheless, the peripheral collisions, so we have these two nuclei that are colliding. In a central collision, they nearly overlap. In a peripheral collision, they only glancingly overlap. And we have seen that the energy loss calculations that I've talked about have worked very well in these peripheral collisions. And nobody questioned that, but that those peripheral collisions in large nuclei colliding, the parameters, the temperature and the size are very similar to these small systems that are colliding, say a proton colliding with a lead nucleus or a deuteron colliding with a gold nucleus. And so we think then that we should be able to apply the energy loss calculations from these large systems into these small systems. In order to verify this claim, we need to look at improving the energy loss calculations that we've done. We would need to include more realistic fluctuations in the elastic energy loss because we're no longer able to trust in the fluctuation dissipation theorem. And we also need to improve the calculations from the Feynman diagram side of the energy loss, where there were a number of assumptions made based on that ordering of scales that I talked about previously that need to be relaxed. So we need to rederive the calculation, rederive the energy loss formula. And this was done by a student of mine, Isabel Colby. This was her master's thesis. She's now faculty at WITS. So she did a great, great job. Here's the result of that derivation that Isabel performed. I don't expect you to understand in this detail other than perhaps to be impressed by Isabel's very nice calculation and to trust me that the calculation works in the way that it should. With one small wrinkle in terms of what's known as color triviality, which is a detail that we don't need to go into, but is very interesting. And when Cole systematically compared his calculations to data, he saw a very good agreement. Now, this is very good in the realm of nuclear physics. Nuclear physics, the parameter that we're expanding in, the strong coupling, is about a third. And so anything within 30% is very, very good because that's the size of the correction we expect at next to leading order, which we have not computed. So looking at a whole host of data, we're able to describe that whole host of data very well with our theoretical calculations. And then what's amazing is that when we apply those calculations to these small systems, we again describe the data extremely well, except for one set of data, which we would like to argue there are certain biases in the experimental measurement that lead to this measurement not telling us what we think that it's telling us. That when one is using experimental measurements to extract certain parameters, as was done with these, say, deuteron gold collisions, then everything makes perfect sense. And the folks who are doing the calculations with the proton lead collisions, we don't think that they made a mistake, but the interpretation needs to be reconsidered. Very good. So that brings me to looking towards the future and what we have to look forward to in the high energy physics realm, and in particular in high energy nuclear physics. So we are here in the beginning of 2025, and at the end of 2025, there'll be another heavy ion physics run where what will be collided is not lead nuclei, but in fact oxygen nuclei. So going from an A of 208 to an A of 30 something, 16, 16. Good. And the point being that we would like to see a medium-sized system, and we would like to understand in detail all of these measurements, all of these observables that I've shown you so far that have been looked at in very small systems and very large systems. Do we see a continuous change of these observables as a function of the nuclear size? Then in the United States, there has been an upgrade of one of the detectors to what is known as S-Phoenix, and this provides precision jet measurements in nucleus-nucleus collisions. The data has been taken and is currently being analyzed. And then going forward, the US, interestingly enough, has committed to retaining its leadership in high energy nuclear physics in the world by constructing the electron ion collider at Brookhaven National Lab. So it will retain the high energy nuclear acceleration capabilities, and then it will add in an accelerator to put electrons into this tunnel and to collide electrons with the nuclei. Why do we want to do this? Well, this will allow us to get a very clean measurement of the nuclear environment, and it will allow us to address questions like where does nuclear mass come from and where does the nuclear spin come from? It's amazing that the proton, for example, has exactly spin 1/2, but we know that the proton is made up of both quarks, 2 ups and a down in the valence, but also a huge number of gluons to hold all of these together. And how does that exact spin of 1/2 originate from those three valence quarks plus all of the C quarks plus all of these gluons? And then also, what are the initial conditions for the heavy ion collisions that I'm interested in? So we talked about how these two nuclei collide, and there's some kind of lumpy initial conditions that are propagated out by, say, viscous relativistic hydrodynamics. And what are precisely those initial conditions? And this machine will give us insight there. It's $2 billion, and it's already started. The ground has been broken, so to speak, with completion aimed for the mid 2030s, and then measurements for a decade or two to come. So there's going to be interesting questions to ask. There's going to be interesting data to analyze and a lot of physics to play with for many, many years to come. That brings me to the end. What I'd like to hopefully have achieved is to convince you that many-body QCD, so the emergent non-trivial dynamics of quantum chromodynamics, is a rich and interesting field with connections to many different areas of physics. The quark-Coulomb plasma that we're trying to study, it's an emergent phenomenon where this field is a field of superlatives. We're creating the hottest matter in the universe, the most perfect fluid, and the largest magnetic fields. And I want to leave you with this question of how big is big enough, coming back to these emergent phenomena and what is required in order to observe emergent phenomena. That in the past we thought it was a mole's worth of stuff. We are seeing in these heavy ion collisions that it seems to be about 50 particles. But in fact, one is seeing that maybe even the number of particles is not 6 times 10 to the 23 particles, 6.22 times 10 to the 23 particles, but it seems like it might even be 6. That you need only 6 particles to start seeing deviations away from particle physics, and that one is going into many-body physics. So power thermodynamics, energy loss, all of these things modified, and there's all sorts of interesting things to come in terms of high energy QCD and the questions we'd like to ask and answer. Thank you very much.
Yeah, thank you very much, Will, for the very interesting and clear talk. Are there questions? There are questions at the back and in front. And then we will ask the people online if they have questions, please.
Hi, Will. Thanks for this nice talk. So just for your future outlook, you mentioned something about the gluon distributions. And So it's been a while since I've been looking into Parton distributions at their PP. So at that time, it was actually not quite clear whether there is even something like a gauge invariant formulation of the gluon angular momentum. So if you don't have a gauge invariant formulation of that quantity, how can you measure that?
Yeah, so I think that has been clarified. So people have gone beyond just Parton distribution functions into GPDs, so generalized Parton distribution functions. And this allows you to gain insight into not only the number of particles, but also what kind of orbital dynamics they have within the hadron. So I think that's there's a whole host of ideas and a giant body of work that has developed over time to answer these kinds of things. I'm sorry? Is this based on the Q had? Yes, exactly. I think that's exactly what one is thinking about, the skew distribution. Various Wigner distributions of quantities of operators and looking at their expectation values within hadrons.
Question here in front, Donovan, please.
Can I ask two quick questions?
Awesome.
So the first is, how difficult is to get your experiment conducted at CERN, for example? Because you need to conduct some experiments in order to study these things, but it's expensive and
very expensive.
How do you convince them to make your experiment?
Good. How do we convince the CERN folks to do the physics that we're interested in? Well, it takes a few thousand people and it takes a few decades. But when CERN was considering the construction of the Large Hadron Collider, they were thinking obviously about fundamental particle physics and the search for the Higgs. And that led to the two general purpose detectors, ATLAS and CMS, which were built specifically to search for new particles. But from the very beginning of the conceptualization of the Large Hadron Collider, they were thinking about other kinds of measurements they would want to do. So one type of measurement you would be interested in, one might be interested in, would be to focus on the bottom quark. And you're interested in the bottom quark because of various symmetries that are very slightly broken in the standard model. And so there's a dedicated experiment to studying bottom quark physics, and that's LHC-B, B for bottom quark. There's also, from the very beginning, an understanding that trying to study the quark-gluon plasma is a very interesting fundamental question. And so there's a dedicated experiment, the ELISE experiment, so for a large ion collider experiment that was part of the original design plan for the Large Hadron Collider, and it was constructed simultaneously with ATLAS and CMS and also LHC-B. So from the very beginning, there was always a plan for the type of physics that I'm talking about here to be conducted at LHC. So it's not like you sort of call up Fabiola and say, hey, can we just put in a little thing in your beam and we'll do some experiments. It's that there's a large collaboration of people who've been built up over time, an enormous amount of expertise, an enormous amount of infrastructure to take measurements. And then there are, and maybe the sort of another way to answer your question is sort of what specific kinds of measurements do people focus on who are in these various collaborations? And that process is an iterative one between the experimentalists who think that, oh, this might be an interesting thing to measure, and theorists who say, I think this might be an interesting thing to measure for these various reasons. And so that's how the procedure occurs currently. The electron ion collider is, while it's being built, the collider itself is being built, but the collaboration to build the detector or detectors is being built up. So that infrastructure is currently being built up. And so white papers are being written where people are saying, these are the golden measurements, these are the silver measurements. And then what type of detector subcomponents will we need to perform those kinds of measurements? And so if this is interesting physics to you or anyone, then there's say, for example, the electron ion collider users group. That is a group of like-minded people who want to influence the direction of the field in terms of what can be done. So I think that was your first question.
Thank you very much.
Yeah. So what was the second
Very
question?
quick.
Yeah.
How do you know the temperature of these particles? Because you cannot measure it. Do you know like the speed, then you compute the temperature or something?
That's such a great question. So how do you know about the temperature of anything, right? So normally in everyday life, we know about the temperature because we got a little metal thing with some mercury in it, and it goes to a certain mark. And we say, oh, okay, so it's 27 Celsius, which means nothing to me as an American who grew up knowing Fahrenheit. But there are other ways that you can measure temperature, and it's all and I talked about this a little bit earlier. So are you a physicist?
No, mathematician.
Okay, well, there's still hope for you. So where am I? Here we go. Oh, I'm going the wrong direction. I apologize. So if you were to take a physics class known as statistical mechanics, let me take a step back. So you've probably taken a physics class at some point in your life, like a classical mechanics class, and you've learned Newton's 3 laws. And you might ask, where did Newton's 3 laws come from? And for the purposes of a first-year physics class, they're taken as a fundamental postulate that F equals ma. And then you can use that law to learn about or to make quantitative predictions about processes. In a statistical mechanics class where one is changing from the idea of following the specific trajectories of individual particles and one is doing a many-body calculation. In principle, one is thinking about many, many, many particles. That's certainly what one was thinking about originally. There's a different fundamental postulate. The different fundamental postulate is that any configuration of the system that has the same energy has the same probability. And if you make that assumption, then what happens is you get out of that a certain prediction for how the system will behave. That a system with any particular energy will be more or less likely in a way that is exactly mapped to the temperature of the system. So the probability that a certain configuration will occur will be e to the minus energy over temperature. For particles, because of special relativity, particles have mass and mass is energy. And so if I scan different particles, these different particles have different masses. And so basically e to the minus the mass divided by some number. If there is a single number for which we get the distribution of particles, and so you can see here, the abundance of protons, which is measured, which is the little dot, and then there's a prediction, which is the line. And down here you have the ratio of the prediction to data. And you see that there's, in general, a very good description of the data using a single value of that e to the minus mass over t, and we'll call that t a temperature because it is a temperature, and that single value is 156 MeV, which is in some units, which is very natural in nuclear matter. And if you convert that to a more natural unit that you're used to, which is a Kelvin or a Celsius, the number you get is a trillion. So that's how you measure, that's one way that you can measure the temperature of some object. Maybe just sort of bringing it back to sort of everyday life, especially out here in Stellenbosch where there's not too much light pollution, you can look up at the sky and you can look at the stars, and you might notice that the stars have different colors. So our star is yellow, but you can look out the sky and you can see red stars and you can see blue stars. And that color tells you how hot the star is. And you're nodding like you've heard of this before. That's exactly what's happening here, doing exactly the same thing. We're basically looking at how hot this is by how often we see some energy. And for starlight, the energy is in the wavelength of the light, and here the energy is in the mass of the particle.
Thank you, Will, for that. Are there further questions here, Rene? Any question from the online audience? Yeah, please, Donovan.
Okay, so there's one question. The LHC experiments generate a lot of data. How essential and effective will machine learning be in expediting the extraction of useful information?
valuable it'll be remains to be seen, but there's certainly a lot of interest in it, and many people are pursuing using machine learning to extract interesting information from this enormous amount of data. I don't know of anything that has come out immediately that at this point is new, but I'm sure something interesting will happen.
Also curiosity, Will, you showed us that in the US, the building of the next generation is going on. How solid is the financial engineering in Geneva? Because
in Geneva,
you show that various stages, yeah, and is the money in the bank or not yet?
It's interesting to me. I thought you were going to ask, given the current U.S. administration, how likely is this to be built?
Describe it as a given fact, so I don't have any reason to doubt it.
Yeah, so this is the funding in Geneva is actually very straightforward, because there are international treaties that have been signed between the various member states where the funding to Geneva is tied to the GDP of those countries. That money is going to flow. So this is going to happen. And then in the US, you might be worried about the current administration, but in fact, if you look at the policy documents that are put out, they very explicitly underline that the national labs in the US are these golden places where science is generated and is world leading, and that technology feeds back into the economy of the United States, and that this should be supported and continue to be supported.
News.
Yeah, very good news.
If there are no other questions here or online, then Will, thank you very much again. And this time I will try not to forget. Usually we give our speakers a little gift.
Oh, thank you so much.
Magazine that NITheCS publishes. Yeah. So,
cheers.
So you can,
so much.
now you can't read it on the way back to UCT because you're driving. Sorry, and Donovan takes the mandatory